a pleasure to introduce Guillermo Peñafort Sanchis, now from UNAM, I think. And he is talking about connect the results of singular map-germs.
Okay, thank you very much. So, yeah, I'm going to speak about what happens to a map-germ whenever you perturb it a little bit. What can happen to the homology of the image if you're looking at dimensions where you want to look at the image, or if not, what happens to the homology of the discriminant if you're looking at the nice dimensions for that. So for instance, if we have this map that takes a plane and makes it into this thing, whenever you perturb it, something like this can happen. And there's a bubble there. And this has homology in degree 2. This is homotopy equivalent to an S2. But if you have a map that parameterizes this thing, this cuspidal edge, whenever you deform it, you can deform it to this same singularity, so homology in degree 2, or you can deform it to this, say, nodal edge or something like that. Anyways, this thing is homotopy equivalent to an S1 because it's homotopy equivalent to just a node. So what happens is, whenever you deform this guy, you will always have homology only in degree 2. Well, in degree 0, you have 1, always, rank 1. But in degree 2, you have something, and never you will find something in degree 1 for this map. But for this map, you can have homology in degree 2 and 1. And I want to explain why this is the case for this map and not for this. And also, the idea is to show the proof of this. We'll use perverse shifts, which is a machine that sometimes is a little bit scary, and hopefully you will find this kind of easy and you will become more friends with the perverse shift machinery. So let me introduce a theorem with a similar flavor to this, which is maybe more familiar to you. It's the Kato-Matsumoto theorem. Well, it's going to be a consequence of the Kato-Matsumoto theorem. So you have X, which is a hypersurface, given by some equation G, in Cn plus 1. So it's an n-dimensional hypersurface. And you want to look at the Milnor fiber. The Milnor fiber, so X is a germ, but the Milnor fiber is not a germ anymore. Is you look, instead of looking at the preimage of 0, you look at the preimage of a small value, delta, and you intersect that with a ball, and that is the Milnor fiber. Kato-Matsumoto theorem says something about the homotopy type, but we want to take a look at the consequences in homology. This would be, it's a consequence of Kato-Matsumoto. But anyways, Kato-Matsumoto. Whenever you're looking at the cohomology, say, of the Milnor fiber, and in this case, it could be any coefficients, but I'm going to put rational coefficients so that it looks more similar to what I'm going to be able to prove in my case. This will be Q in degree 1, and then there will be a bunch of zeros. Okay. What they say is, call D the dimension of the singular locus of X. Then when you look at the Milnor fiber, it will be connected. Then there will be a bunch of zeros from, sorry, this is 0, from 1 to n minus d minus 1. And then something else from n minus d up to n. And then zeros here and zeros here. So what they say is the homology has to vanish in this range. You can only find homology from middle dimension d positions to the left. Okay? Okay. So in our case, we want to look at map-germs. So I need to introduce a little bit the objects. So we're looking, instead of looking at hypersurfaces, I will look at multi-germs. Oh. I hope this line is not necessary for anything. I will look at multi-germs. So I will take something, Cn, S. S is a finite set. And all the points in S are mapped to 0. So this is like, say, a germ with several branches. That is how you put these several branches here. Okay. Then we want to look at the discriminant. So first, the critical set. Is the set of points where the differential is not surjective. And the critical set and the discriminant is the image of the critical set. And we are going to work only with k-finite maps. K-finite means that if I restrict to the critical set, I have a finite map. So an observation is that if P is less than n, then the critical set is the other way around. If P is bigger than n, then the critical set is all the source. And the discriminant is just the image, because the differential just cannot be surjective. So, and in that case, k finite is equivalent to finite. So in the case that P is greater than n, we are looking at these kind of pictures. We were looking at the image. If not, we are looking at the discriminant. Okay. And then we want to look at deformations. Okay, just one more thing. If P is less than or equal n plus 1, this implies that the discriminant has dimension P minus 1. It is indeed a hypersurface. And, okay. So we want to look at deformations of these guys. What is a deformation? Well, what we look at is an unfolding. An unfolding is just a map germ of the form ft, comma t, where f0 is f. Okay? And now I want to say what would be the corresponding object in this theory to the Milnor fiber. The Milnor fiber is not a germ. It's a global object. So we need to define what would be our global object. What we do is to take a good representative of the unfolding. And this definition, I'm a little bit scared of giving this definition because Terry Gaffney is here and he has a definition of good unfolding and it is a little bit different. But in this generality, this should be the adequate definition, at least for me. This means you take an unfolding, you take a representative of your unfolding, and you want to ask one that if you look at the discriminant, is the locally trivial vibration. If you look at the discriminant coming to the parameter space, is the locally trivial vibration of course not on the whole parameter space, but once you remove the origin. Okay? Then you want to ask that the discriminant, sorry, I'm going to call this pi. The central fiber has to be contractible. And 3, the discriminant retracts to the central fiber. So this is not the usual definition of good representative, but whenever you choose a good representative in any sense that I have seen, you will find the same homology as if you take this. And this you can take in more general situations than the usual definition. So this, you will have one of those every time. Whenever you deform, you can find a good representative in this sense. And then a perturbation is just fix any of the parameters and take the map, F delta. Okay? But the parameter, of course, cannot be 0. So choose any non-zero parameter and fix your F delta. This is what I mean with a perturbation. These are the perturbations. These are perturbations here. Okay? So what is the theorem? The theorem, and this is a collaboration with Matthias Sack and Jonkyang Liu. So with Matthias Sack and Jonkyang Liu. Is this. Well, I'm going to assume that the maps are k-finite, okay? So I'm not going to even write it. Oh, no, wait. Before this, I need to define what is the instability locus. So what is a stable map? A stable map-germ. Well, this I'm going to define, I'm going to skip some details, but stable means that every unfolding is the trivial unfolding after changes of coordinates. So for instance, if I take a map that parameterizes this cross, I might deform it to something like this. But I can change the coordinates so that this deformation is trivial, and then I'm doing f times the parameter. But if I take a map that does this, then I can deform it into something like this. And there's no way I can change the coordinates so that this is a trivial unfolding. Okay? So this is unstable. The previous thing was stable. And then the instability locus, oops. is the set of points y in the target such that f, and then you look at the preimage of y and you intersect it with the critical set. And this has to be a finite set because your map is k-finite. So whenever you restrict to this guy, the map is finite, and then this fiber has to be finite. This is a finite germ, is not stable. That is why it's called the instability locus. And well, whenever you're looking at something k-finite, this guy is analytic. And now I can say, okay, let me just say who are the instability locus in these cases. In this case, it would be this point, because away from the instability locus, the only thing I see is a regular branch of a map, and that is stable. But if I look here, this is the instability locus. Okay. So now I can state the theorem. The theorem with Sack and Liu is let D be the dimension of the instability locus then, well, there are two cases. If P is smaller than or equal to n plus 1, then you have the same thing as in Kato-Matsumoto. Cohomology of the discriminant of a perturbation is Q coefficient is going to be Q, then zeros from P minus 1 minus D from 0 until P minus 1 minus D. This is the dimension of the discriminant, and then you go D steps. No, here is where you go D steps. So from P minus 1 minus D until P minus 1. Here is where all the interesting homology lies. So you see, in this case, the instability locus had dimension 0. So that means that I can only have non-trivial homology in middle degree. I cannot move to the left of middle degree. But in this case, the instability locus had dimension 1. So I'm able to move to from middle degree, which is 2, I can move 1 to the left. And I have perturbations that produce homology in degree 2 and perturbations that produce homology in degree 1. Okay? And then if P is greater than n plus 1, something else more complicated. Something else, but you have an analogous result, but it's much more difficult to write, and we are going to skip it just to save time. Okay, so how do we prove this? Well, we need to use the machinery of perverse sheaves. There's a very easy proof of Kato-Matsumoto with perverse sheaves, of this consequence of Kato-Matsumoto, and you will see that the same thing proves our theorem. So let me introduce this machinery. I think I'm going to erase maybe this. So the machinery of perverse sheaves works within the derived category of complexes of sheaves. So what is that? So this is something, all right, this, and the element, an element here, I will write as a sheaf, but what that is a class of a complex of sheaves with differentials. Okay, there will be some differentials here. Okay, these are the kind of objects. I'm not going to define anything here. Okay, and now I'm going to introduce the notations of cohomology that I use. So whenever I write this, we were happy with this before. This means usual cohomology, usual singular cohomology. Cohomology with Q coefficients. Then whenever you have one of these guys, you can take a point and you can compute go to that point, produce the stalk, you will have a complex of modules, and you can compute the cohomology. That is called the stalk cohomology. And I will write it with this calligraphic H. And you have to fix a point because you're going to take the stalk. It is just that. It is, no, not this. The kernel of the differential of K over the image, no, it's K plus 1 here, image dx K, okay? So it's just go to the level of stalks and compute cohomology. And then there is the hypercohomology. The hypercohomology is something else. And it's like this. This is hypercohomology of this space with coefficients on a sheaf, a complex of sheaves, really. The only thing you need to know about this guy is that if I take the constant sheaf and I compute hypercohomology, and my space is not something crazy, is, for instance, an analytic space, I will be computing usual cohomology. So if I take an analytic space, and I take the constant sheaf on it, and I compute this guy, whatever it is, what this guy is doing is computing usual cohomology. That is because I chose a very simple sheaf. Okay? And now, in this category, if X is analytic, there is the category of perverse sheaves inside this. And it is just a subcategory of the derived category, which we don't know very well what it is, and we don't know very well what this subcategory is. But we are going to work with this. Just okay? There's a subcategory, so some of these guys are perverse, some are not. Okay? And the important thing about perverse sheaves are two things. It is if X is a locally complete intersection, and the dimension of X is n, then whenever I take the constant sheaf on X and I shift it by n degrees, remember this is the constant sheaf, and I'm looking at this as the sheaf, and then zeros to the left, zeros to the right, so that it looks like a complex of sheaves. Well, if I move it n positions, I never remember very well in what direction, but then this guy is perverse. provided that I started with a locally complete intersection. Okay? And there's another thing that we are interested in, which is if F is perverse. Oh, I need to define the support, sorry. The support of a sheaf, a complex of sheaves in the derived category is the points in X such that whenever I compute cohomology, Stolt cohomology is different from 0 for certain K. So there's a K, there's a K such that this Stolt cohomology doesn't vanish. Okay? That is the support of a sheaf. So a very important thing about perverse sheaves is that if I take a perverse sheaf and D is the dimension of the support, then the Stolt cohomology of F is concentrated in certain degrees. For any X, for any J, the only degrees where I can have not zero cohomology are between 0 and minus D. For some reason, the people that work with perverse sheaves, they like to put the non-trivial cohomologies starting from 0 and then going to the left. Okay? So whenever I have a perverse sheaf, I look at the dimension of the support, and I know that the Stolt cohomology has to be concentrated from 0, D positions to the left. It's very similar to Kato Matsumoto thing. You know? It has this flavor, and also this flavor, right? Okay, and then there's the vanishing cycles, and this is the last piece of information. The vanishing cycle functor so you're given an analytic function, call it H. This is analytic. And then the vanishing cycle functor is a functor that, if you're restricted to the perverse sheaf category, it takes a perverse sheaf on X to a perverse sheaf in the central fiber. Okay, very good. And what it does? Well, one thing you have to know, in the derived category, you don't expect to understand what the objects are. What you have to hope for is to understand what the Stolt cohomologies are, or what the hypercohomologies are, but not more than that. So what is the Stolt cohomology? The Stolt cohomology of the vanishing cycle functor applied to a perverse sheaf F on a point X is going to be the relative hypercohomology, which I didn't define, but so you will take a small ball of radius epsilon on X, and then you will take the same small ball, but intersected with the fiber, a fiber near the origin. So you will take a value delta, small enough. You will look at the fiber of delta. You will compute this relative cohomology with coefficients in your sheaf. Okay? What is relative cohomology? relative hypercohomology. Is the natural thing that fits in the long exact sequence that you expect, okay? Okay, this is all we need. So let me prove Kato-Matsumoto using this stuff. And I'm sorry, I did something. HK, so the stall cohomology in degree K. And here, there's conventions. There are two conventions. You can shift this guy, or you can define it already shifted. I'm going to define it already shifted because you need less symbols to write in that case. So it is shifted, okay? Whenever I compute the stall cohomology of the vanishing cycle functor applied to this, at degree K, I will obtain some hypercohomology in degree K minus 1. Okay. So proof of Kato-Matsumoto. We're given, it is already there? Yeah, it is still there. So let's apply the vanishing cycle functor to this G. Let me see. I have G from Cn plus 1 to C, right? Okay. Well, Cn plus 1, it is a complete intersection, right? So the constant shift of on Cn plus 1, if I shifted n plus 1 positions, this is a perverse shift on C n plus 1, right? And then we don't know what this guy does exactly, but we know that if we apply it, we will obtain a perverse shift on the central fiber. Right? So let's apply it. So this has to be, whatever it is a perverse shift where? On the central fiber of G minus 1 of 0. That is exactly X. Right? Now let's see what this stall cohomology is. All right, compute this guy. It's K of, oh God. And I computed on a point X. Well, this is this relative hypercohomology. There will be a ball here, X, and the ball on X intersected with the preimage of a nearby value with coefficients on this shift, right? And there's a minus 1 here. I will probably fail with the indices because it's a mess to keep up with all this, but you have to know that the indices, they have to fit. If not, there would be counterexamples to the theory or to the theorem of Kato-Matsumoto, and well, okay? Now, the shift, you can put it here right away. And then we will be computing hypercohomology, relative hypercohomology of the constant shift. But that is usual relative hypercohomology. So this will be usual relative hypercohomology of is ball. Oh, and of course there's no, this will be a mess. Well, hopefully it's this. No, it is this. With rational coefficients, right? But now, whenever I'm computing this relative hyper, no, it's not hyper anymore, relative cohomology, well, this is contractible, okay? So this is isomorphic. If I write the exact sequence, there's a lot of zeros, a lot of isomorphisms, and this relative cohomology is always this cohomology, but in degree 0. In degree 0, it changes by 1, right, in the rank. So this is what is, by definition, the reduced cohomology of whom? Of this guy. And what is this guy? Let me write it as Fx. It would be the Milnor fiber, but on a point of G on a point X. Right? Fx is the Milnor fiber of G at X, right? But anyways, if I look at the regular point, what is the reduced homology? It's nothing, right? Because on a regular point, the Milnor fiber, it is regular. And when I do reduced cohomology, it is 0. So what I know is that the support of this stuff here, the support of this sheaf, has to be contained in the singular locus of X, because on regular points, there is no stalled cohomology for this sheaf. Okay? Okay, and that is all we need, because now, if we let D be the dimension of this singular locus of X, now we are going to apply something. Here. Okay? But we are going to apply it on 0. If I want to compute the reduced cohomology of the Milnor fiber, well, that is exactly the stalled cohomology of my guy. I need to put some. Oh, well, let me ignore the indices. You know that they have to fit because this is a well-established theorem. Okay. This is exactly the stalled cohomology at the origin. Right? And since the support has less dimension than D, then I will apply that stuff. And I will get exactly what I wanted. There's a bunch of zeros, and then there's the rest of the stuff. Okay? And this is the reduced cohomology, so if I remove this tilde here, I get a Q here. Okay? So this is the proof of Kato-Matsumoto. Now let's do our theorem. 4 minutes. So instead of applying that to G, apply it to this mapping. You take the discriminant, and you go to the parameter space. You put here discriminant. You shift by the right dimension, which, since this is the unfolding, so the discriminant has one more dimension. So it's not p minus 1, it's p. Here there's a discriminant. Here. And then you have to believe me that if I go to the discriminant and I look at the central fiber, it is the discriminant of the original map you started with. There's a discriminant here. This is, let's call it G. Okay. This is the discriminant. Discriminant P. Discriminant. No, sorry, this was okay. Discriminant P. There's a P minus 1. Well, I mean, we already ignored this before, right? Of course, now it's not the Miller fiber. Let's just leave it at this. Okay? This is, so this is discriminant intersected with the ball. And this will be the discriminant of F delta with the ball with coefficients, with rational coefficients. And now, if you believe me, if you are away from the instability locus, this guy is a trivial family of the discriminant of the original F cross C, right? It looks like this. Away from the instability locus, any unfolding is the trivial unfolding, and its discriminant looks like this. And when you look at the perturbation, you're looking again at this, and this relative cohomology has to be 0. So what we have in this case is that the support of this stuff, the shift we're working with, is contained in the instability locus. And we want to compute this cohomology of the discriminant of F delta, and that is exactly this thing at 0. And then you get the result. So it's just more or less the same proof applied in this context. And that's all. Thank you very much.